Okay, so today we're going to talk about where sine waves and cosine waves actually come from. Now, last week we were talking about radians, and we've been spending a lot of time with the unit circle, and you've also seen these a little bit in Algebra 2. But we're going to see if we can shed a little bit more light on exactly what these graphs are and where they come from. So what I have here on the screen is a space for the unit circle and a horizontal bar that's going to be our x-axis. Except we're not really going to call it an x-axis right now. We're going to call it a theta axis. You know, theta like an angle on the unit circle. It's kind of interchangeable with x, but I'll show you what I mean in a minute. So what I've set this graph to do is, as I change values for theta, two things happen. One, my graph starts drawing the unit circle. And two, my graph does a little something different down here. So let's talk about what it does. Now, here we are. Let's say we just go up pi over 6 on the unit circle. Now, as you guys should know, what that means is we've gone up 30 degrees. All right? Degrees are a man-made construction. Radians are something a little bit more real. Okay, so when we know when we've gone up 30 degrees, you guys should know that the sine of 30 degrees is 1/2. And we always say that sine corresponds to the y value. What that actually means is when you've gone 30 degrees, a third of the way up to the top of your circle, you've gone exactly halfway up to the top of your circle. This is a unit circle, meaning a radius of 1. So you're halfway there by height. Okay, you're not halfway there by horizontal change. What you're actually doing is walking the length of this circle. So what a sine wave does is it measures the same heights. Okay, so when you've gone 30 degrees, which is pi over 6 radians, you're at a vertical height of 0.5. Same thing down here on my sine wave graph. You're also at a vertical height of 0.5. But how do you know how far out to go on your axis? Well, remember what a radian actually is. A radian is the physical distance that you walk around a unit circle when you get to these angles. So pi over 6 radians isn't just a funny way to say 30 degrees. It is the actual length of this arc. And if we take this arc and lay it down on the x-axis, okay, this is exactly how far we've gone. So yeah, the x-value coordinate here is pi over 6. That's also the length that we've walked along this circle. So what a sine wave does is it takes the circular motion of walking around a circle and lays it out on a horizontal axis. So as we keep going here past 30 degrees, we get higher and higher, and when we get to 90 degrees, okay, that's where we hit the top of a unit circle. That's where sine wave hits its maximum value. That's where the sine hits its maximum value. Cosine is up and down on the unit circle. So at this point, we've hit a value of 1. It stands for 100% as high as you can go. On the sine wave, we've also hit a height of 1. And remember what radians actually are. Going 90 degrees around a circle is walking a physical distance of pi over 2 radians, pi over 2 lengths, units along this arc. Okay, so that's been mapped down here to be pi over 2, which is about 1.57 units down this horizontal axis. That's where we put this peak. Okay, now as you know in the unit circle, if you keep going past 90 degrees, you start to go down. And when you've completed your semicircle at 180 degrees, or pi radians, that's when you've walked 3.4 units along your circle. You've started at a height of 0, you've gone up to a height of 1, you've come back down to a height of 0. Same thing on the sine wave. As you walk 3.14 or pi units along this horizontal axis, you start at a height of 0, you go up to a height of 1, you come back down to a height of 0. All right? I know this doesn't look semicircular, but that's because we've taken this arc and we've stretched it out straight along this axis. Length of this arc is what corresponds to this length on the axis. That distorts the shape of what would otherwise be a circle. Okay, so we keep going past 180 degrees. We keep going around our circles. Okay, and the sine still represents the height. Except now the height is below the x-axis. It's negative height. It's depth, if you'd like. So the sine wave, which again started at 0, peaked at pi over 2, hit 0 at pi, the sine wave also goes below the x-axis. So this is 5 pi over 4 units, this length along the axis. That's when you've walked an arc of 5 pi over 4 units, which, if you were paying attention last week when we converted radians to degrees, is 225 degrees. So at that point, we're down below the x-axis, and when we get to 270 degrees, this depth of 1 on the unit circle is also a depth of 1 on our sine wave. And just as we've walked 3 pi over 2 radians around the circle to get to this 270 degree angle, we've also walked 3 pi over 2 radians along this straight line. Finish up our circle here. Oh, that made the graph jump in interesting ways. Let's go back. So to finish up one time around the circle, 2 pi radians is the same as 360 degrees. That's when you've walked a physical distance of 2 pi. 2 pi times the radius of 1. It's also the circumference of this circle. Okay? And when you've walked that length along this horizontal axis, you'll have gone from a height of 0 up to a height of 1, back to a height of 0, down to a height of -1, and then back up to a height of 0, and here we are. Now, on the circle, as we've discussed, we can keep going. We talked about coterminal angles. Angles you wind up at the same spot. It's just you've already gone 360 degrees. Because you can still keep walking along the circle more than one revolution, you can keep walking down your horizontal axis here more than 2 pi units. And as you do that, the pattern just keeps repeating. So at this point up here at 90 degrees, I've walked once around the circle and another quarter circle. That is 5 pi over 2, or 450 degrees. I didn't think a minute there. And that means I've walked 5 pi over 2 units down the x-axis. As I keep going around my circle, another half revolution, that's 3 pi radians, that's 3 pi units down here. And once again, I've repeated the top half of my cycle, of my periodic motion, of my sine wave. I've gone from the middle up to the peak, back to the middle. Same thing as I start my second time around the circle. And as I finish a second full revolution of my walking around my circle, my sine wave finishes a second period. This should look like 2 identical halves of the same shape, because it is. A period of a sine wave is the same as 1 revolution around a circle. Meaning, just like if you keep walking in circles, nothing changes, if you keep walking down this horizontal axis following this sine pattern, you'll repeat yourself. You'll go middle, up, down, up, middle, down, middle, forever. Just like walking in a circle will do. Now, let's talk a little bit more about what some of this might mean, and let's give me a little more room here. Okay, so I've set this up to draw this second vertical line at a height of 0.5. Okay, let's see if I can make that a little bit bigger on my screen here. And what this refers to, here's what I want to talk about a bit. Remember, sine on a unit circle is how high you are. Same thing down here. The height on the unit circle is the height on the sine wave. Okay? Now this unit circle passes through a height of 0.5 units 4 times in 2 revolutions. It's when the unit circle, when walking around the unit circle, would take you through these points. Okay? So, as you know, you first get to a height of 0.5 at 30 degrees. Second time you get to a height of 0.5 is when you get here to 150 degrees. Now, if all you care about is the height, how high you are above the x-axis, there's really no difference between these 2 points. If your only goal in life is to be half a unit above an x-axis, 30 degrees, 150 degrees, pi over 6 radians, 5 pi over 6 radians, either will serve you perfectly well. If, while you're at this height of 1/2, you need to know whether you're looking left or right, well, at 30 degrees, pi over 6 radians, you're looking 30 degrees to the right, and at 5 pi over 6, 150 degrees, you're facing 30 degrees to the left. Does that matter? I don't know. It depends on what you're modeling. And we'll talk about how we use this to model real-life situations Wednesday. Start talking about that. But let's keep going around our circle. And we're down here. We're never going to hit a height of positive 0.5 down beneath the x-axis. But we come back up above the x-axis to a height of 0.5. And boom, here we are. Now this looks like our 30-degree angle to the right again. And it is. No difference. But notice on the sine wave, there's a big difference between having walked pi over 6 units and having walked 13 pi over 6 units. For one thing, you've walked 13 times as far to get to the same spot. Now, does that really matter? I don't know. If you're spinning a bottle for a childish game, it doesn't matter. Bottle winds up facing 30 degrees to the right. Doesn't matter how many spins it took to get there. If that's all you're modeling, then there's no difference between 30 degrees and 390 degrees. However, what if you're modeling something like, I don't know, the human neck? I think there's a slight difference between looking 30 degrees to the right, spinning my head 30 degrees to the right, and, I don't know, spinning my head 390 degrees to the right. For example, in one case I'll survive, in the other case I won't. So if you're modeling human neck motion, I suggest you not go past maybe 180. We can keep going out here to 17 pi over 6, also at a height of 0.5. And again, if all you care about is being half a unit above the x-axis, all of these points are indistinguishable. There's only 2 possible places to do it, and the fact that there's 4 on the sine wave seems a little silly. But if you're in a situation where you have to know the difference between rotating 30 degrees or 150 degrees or 390 degrees or 510 degrees, then yeah, you need a sine wave to tell you how many rotations you've gone. Again, it just depends on what you're trying to model. So that's where a sine wave comes from. Now let's talk a little bit about where a cosine wave comes from. And let me reset my graph for a moment. Now it's very similar, okay? It's a very similar idea, except one thing that some kids sometimes struggle to get their heads around. My dog in the background is bored because she already knows all this. So, as you know, sine on a unit circle represents up and down. Cosine, as you should remember, represents how far you are to the left or to the right. So when we graph a cosine wave on this horizontal axis, this height no longer represents up and down. The height on the cosine wave represents how far to the left or right you are. So we're taking this idea of being right or left, and we're mapping it onto a graph where it now means up or down. So before we even start, when we're at 0 degrees, which as you remember on a unit circle means horizontal and to the right, okay, at 0 degrees, you are 100% 1 full unit to the right on this graph. That means a cosine wave starts at 1 unit high above the x-axis. Because again, we're taking this horizontal distance and we're mapping it into a vertical representation. Now, as you know, as you start going around the unit circle, see, as you go from 0 up to, say, 30 degrees again, what you've done is you've shrunk this horizontal distance. If you start at 0 degrees and you walk your pi over 6 radians up to 30 degrees, okay, you're getting closer to the y-axis. This horizontal distance is shrinking. So on the cosine wave, that means your height is lowering. Horizontal distance up here becomes vertical distance down here. So as we go past 30 degrees and get closer and closer to the y-axis eventually touching it, our cosine wave starts 1 unit above the x-axis and eventually lowers itself to 0. Again, this doesn't look circular because we're taking this arc motion, we're taking this walk along a circle and stretching it out into a perfect horizontal distance of the same length, 1.57 or pi over 2 radians. So that's going to distort the shape a little bit. Now, when you get past 90 degrees, you're now to the left of the y-axis. Your horizontal distance is to the left. So right is positive, left is negative. Down here, negative means you've gone under the x-axis. To the left of the y-axis on the unit circle means under the x-axis on the cosine wave. Stay with me here. Now when we get to 180 degrees, meaning we've walked pi or 3.14 units around our circle, that's where we're 100% to the left. 100% to the left is represented on the cosine wave by 1 full unit down below the x-axis. As we keep going past 180 degrees and get closer to the y-axis, our side-to-side distance is shrinking. Our cosine wave goes back up to 0. So when you've walked 3 pi over 2 radians around your circle, you've moved 3 pi over 2 units down this horizontal axis, and you've started way to the right, wound up in the middle, wound up way to the left, wound up back in the middle, and as you complete your circle, you're back all the way to the right where a cosine wave begins and where it ends. Once around the circle is also 1 full period of a cosine wave. And again, you don't have to stop there. You can keep going around your circle, and as you do, you will simply map out a second cosine wave with the exact same shape and behavior. Okay? 1 period of the cosine wave, 2 periods of the cosine wave, because you've gone around the circle twice. Now, I've also set this one up to illustrate how different heights behave. Once again, I chose 0.5 as a height, 1 unit above, half a unit, above the x-axis. As we can see, same idea. We get these 4 points on these 2 periods of a cosine wave that are all half a unit above the x-axis, which means they're all half a unit away to the right of the y-axis on the original unit circle. It's easy to get mixed up. Apologize for the confusion. So if all you care about is being half a unit to the right of the y-axis, these 2 points are identical for your purposes. And these 4 points are completely redundant, if that's all you care about. If you care about whether you're facing up or facing down, by the way, in the cosine wave, as you might remember, this horizontal distance of 0.5 occurs when the reference angle is 60 degrees. So if all you care about is facing 60 degrees up, then pi over 3.5 works fine, and so does 7 pi over 3.5. 60 degrees and 420 degrees. They both wind you up here. If all you care about is looking 60 degrees down, 5 pi over 3, or 300 degrees, or 11 pi over 3, 660 degrees, both equally fine. Doesn't matter how you got there, if that's all you care about is where you wind up. Again, if you're talking about something with a limit to the rotation, I keep going back to the most visceral example, the human neck. Doesn't spin 660 degrees. Wouldn't want to spin at 300 degrees. In fact, you're pretty much stuck at 60. It's about as far as you're going to go with that one. It's about as high as you're going to look up. So, does it matter which point you use if you want to be at 0.5, looking 0.5 away from the y-axis, looking up at a 60-degree angle? Depends. Depends on what you're modeling. And again, we'll talk more about modeling specific things that fit these curves nicely more in 2 days. Okay, so that's where they come from. That's enough to get you started in the discussion tonight. And tomorrow I'll have a video up for you to watch on how to move these things around. What do you do when you don't want a nice, neat cosine wave like this? You want a cosine wave that maybe is shorter or taller or stretched or doesn't line up perfectly with the origin. That's what we'll talk about next.